Okay, so you're able to see,
Yes, sir.
Yes, sir.
Yes, sir.
You
So
can
in
see
the
it, sir.
last class, I forgot to show this genetic algorithm toolbox in the MATLAB. So in the MATLAB, this toolbox is there where you can use genetic algorithm instead of the previous F minimum con. Okay. So all these things are the same. Objective function, then you have to give number of variables in the genetic algorithm. Like if it is x and y, then you have to put two variables. X, y, z is there, then 3. Then A, B are the linear inequality constraints. A equality, B equality are the linear equality. Then lower bound, upper bound, then list of non-linear constraints. Okay, so this is exactly the same as for the F minimum constraint. Only thing is that instead of using calculus-based method, you use GA, and some examples are shown here, like finding the maxima of this with this toolbox. So actually, this MATLAB genetic algorithm is a minimizing genetic algorithm. So if you want to do maximization, you have to take the negative of this objective function. Okay. So the range of x and range of y is there. Population size is 200. Crossover rate is 40%. The number of generation is 100. So all those things are indicated here. Okay. So tolerance is this much. Population number of generations is 100. Population is 200. Crossover rate. Then this is the definition of the objective function. Then all these things are done here. Okay. And you will get the right answer. Okay. You will get the correct answer. I think we can stop this here because you already looked at the a lot of examples for genetic algorithm. Okay. So we'll go to next topic, that is multi-objective optimization. Okay, which is more important. Okay, so next we go to multi-objective optimization, which is a highly important topic in engineering. Okay, so all engineering problems like a brake optimization, clutch optimization, gearbox optimization are all multi-objective in nature. So what is meaning of multi-objective optimization? So concept of multi-objective optimization. So in many engineering problems, we need to minimize or maximize two or more conflicting objective functions. Okay, for example, in a bridge or in an automotive structure, we want to minimize structural weight, and at the same time, we want to maximize the stiffness. Or in a industrial engineering problem, we want to minimize the cost of the equipment and at the same time maximize the strength, which is conflicting. So these objectives are conflicting. The optima of these objective functions will not coincide at the same point in the feasible region. Okay, so this is the simple and easy to understand problem of multi-objective optimization. So this is the feasible region. So this is objective function 1. I want to minimize objective function 1. So that is occurring here. Okay, so x1, x1 star, y1 star. So that is the minima of objective function 1 alone. Okay, that is to minimize cost. Okay. And next is I want to minimize, okay, maximize strength means minimize 1 by strength. Okay. So another objective function is to minimize 1 by strength. So that optima occurs in totally another location. Okay, that is x2 star, y2 star. Okay, so if you want to minimize cost alone, then this is the solution. If you want to minimize the 1 by strength alone, or if you want to maximize strength alone, then this is the solution. So if you want to minimize both these objectives, both these objective function, what is the solution? Okay, does it occur here or here or here or here? So that is what we are going to look at. Okay. So actually the concept of multi-objective optimization is little bit difficult. So I'll illustrate it with simple example. Okay, so minimize two objective functions. So first is this objective function f1. It is actually radius of the circle centered at 3, 9. The next is also minimize another objective function f2 whose center is at x is equal to 3 and y is equal to 12. Okay, so this is the feasible region. Okay, feasible region is this. So x is equal to 6 is here, y is equal to 4. Okay, so this is the feasible region, and we have to draw the contours of the two objective functions. So what will happen is that, so these are contours which are starting from a circle centered at 3, 9. Okay. Okay, so it will touch here. So if you look at these objective, okay, 3, 9. Okay, so these are contours of objective function centered at 3, 12. Okay, so these come like this, and they touch at exactly the same point, x star, y star. Okay, so you can see that for this example, although we have two objective functions, their contours are hitting the feasible region at one point. So in this type of problems, there is no conflict. Okay, this is the same thing. So objective function is centered at 3, 9. Another is objective function centered at 3, 12. So the contours will hit the feasible region at 3, 4. This is 3, this is 4. Okay. So, okay, f minimum 5, f1 minimum is 5, then f2 minimum is 8. Okay. So, for cases like this, there is no problems. Okay, because both the objective function contours are touching at the same point. Okay, so here we have one unique solution satisfying both objective function. But this situation is very rare. Okay, if you have two objective function, it is highly unlikely that their contours will touch the feasible region at exactly the same point. Okay, so this is a unlikely case. So let us look at another case, which is the more likely case. So what we do is that we shift the center of the second objective function so that the contours are coming from another direction. So now the two objective functions contour will touch the feasible region at different locations. Okay, so this is f1, our old objective function. So that will touch the feasible region at 3, 4. So we changed the center of the second objective function. Now the contours are coming from the on the right hand side, and they are going to hit the feasible region at 6, 1. Okay, so now our problem is starting. Okay, so if you look here, you can see that minimizing f1 and f2 give two different solutions, A and C. So A will minimize f1, C will minimize f2. But if you want to minimize both f1 and f2 at the same time, which point should you select here? So that is what we are going to see. Okay, so we get 2 points A and C. This point A minimizes f1. Okay, because f1 is only 5 and f2 is 7.6. And point C minimizes f2 because f2 is only 4, and now f1 has become 8.5. Okay. So you can pick many other points here, B, A, B, D, etc. If you take the point B, the value of f1 is 5.8 and value of F2 is 4.9. If you take a point D, it is equidistant from F1 and F2, 6.1 and 6.1. So which of these points will satisfy, so which of these points is closer to both F1 and F2 at the same time? So that is the main challenge of multi-objective optimization. You have to find a point X which is close to both F1 and F2. Okay. So the concept of dominated and non-dominated points are designed to address these questions. Okay, so now you consider this multi-objective optimization problem. Minimize F1 of xy, F2 of xy, subject to some feasible region. Okay, so this is the feasible region, and it is a two variables are there, x and y. Okay, so this is called design space because x and y are the design variables. So now the feasible points in the design space are mapped into the criterion space or objective function space. Criterion space is nothing but objective function space, where on the x-axis you have f1 x of y, and y-axis you have f2 x of y. So what you do is that every point here x1 y1 has to be converted to f1 f2 coordinates. Okay, how do you do that? Okay, suppose this is 5 10. So you have to find f2 5 10 and f1 5 10. Okay, so it is converted into the two objective function values. Okay, some another point is there like 1 2. Okay, so here you find f1 f2 1 2 f1 1 2. So this point is transferred here. So in this manner, every point here is converted to f1 of 2 coordinates. Okay, so eventually all the points here x1 y1 x2 y2 x3 y3 are converted to f1 of 2 values. So you get a cloud of points. Okay, so this entire feasible region has infinite number of points, and all these things are transferred to infinite number of f1 of 2 points. Okay, so now we have to study the concept of dominated and non-dominated points. So actually you have to remember that we are going to minimize f1 and f2 both. Okay, so let us take a point A89. A89 means f1 is equal to 8, f2 is equal to 9. So A is called a dominated point. Dominated means you are being dominated by a superior person. So there is some other points which are superior to A, and A is being dominated by that superior point. So which are the superior points which are dominating A? So all these are the superior points. So they're better than A because their f1 of 2 values are lower than A. So let us take this point B. So the coordinates of B are 6 7. So f1 is equal to 6, f2 is equal to 7. So you can see that the f1 of 2 values of B are lower than f1 of 2 values of A. So for A, f1 is equal to 8, f2 is equal to 9. So 6 is less than 8 and 7 is less than 9. So B has minimized f1 of 2 better than A. So B is better than A. And another point, if you take, okay, R. So this point is R. is better than B. Okay, because the F1, F2 values of R are much lower than that of B. So the lower you go, better the points, because they have smaller values of F1 and F2.
Sir, in case of maximization problem, it should be opposite, right, sir?
Now that we'll see later. This is for
Okay.
minimizing F1 and F2. So minimizing F1 and F2 means you have to go like this. Okay. Okay, maximizing you have to go like this. That we'll see later. So if you look at this sector, it's in the direction of bottom left. Okay. Bottom left direction. Okay. Okay, so as I said, you can go down and down. So E is better than A because the F1, F2 values of E are lower than A. Okay, so you can keep on going down like this. Okay. Okay, and finally, as you go down like this, you will hit this last row of points, or the locus of the last set of points. Okay. So these are called non-dominated points. Okay. The reason it's dominated is that if you take this point here, you cannot find any other point having a lower F1, F2 value than this point. Okay. So if you take another point here, okay, you cannot find any other point below this having lower F1, lower F1, F2 value. And same here. Okay. So if we take a point P here, you cannot find any value of the any points below P having a lower F1, F2 values than P. So each of these points have a unique F1, F2 value, which is one of the lowest possible combinations. Okay, so the locus of all these unique points is called Pareto optimal front. So each point is a unique combination of lowest possible values of F1 and F2. Okay, so let us take this point. Okay, so here, say F1 equal to 3, F2 is equal to 10. So if you draw, okay, F1 is equal to 3, F2 is equal to 10. So you cannot find any point here having F1 less than 3 and F2 less than 10. So this combination 3, 10 is a unique low combination. Similarly, if you come here, okay, F1 may be 5, okay, F1 may be 5, F2 may be 8, okay. So you cannot find any point here whose value F1 is less than 5 or whose value F2 is less than 8. So 5, 8 is a unique combination. Okay. So any point in this lower curve gives a unique combination of low values of F1 and F2 which cannot be improved. So the locus of all these points is the Pareto optimal front. So our goal is to obtain this Pareto optimal front by filtering out the dominated set. So this is the dominated set. Dominated by all these non-dominated points. So what will happen in the genetic algorithm for multi-objective optimization is that it will start from here and it will slowly eliminate all these non-dominated points and finally it will reach here. Okay. Okay. So significant computational effort is usually required for this. Because then another important thing is that each of these non-dominated points is a unique or equally good solution to your multi-objective problem. So if you want to minimize F1 and F2 subject to say G1, H1, and you get this locus of points, then you have infinite number of solutions. Okay, all these are infinite number of solutions, and each point is equally good as the other point. So it is up to you to choose. Maybe you can choose this point if you want to have a moderate value of F1 and F2. You can choose this point if you want to have a small value of F1 and large value of F2. So it is up to the user or engineer to pick any of these points. So all these are solutions to this multi-objective problem. Okay. So what constitutes the Pareto optimal front? Where does this boundary come from? Okay, so where does this boundary come from? Why does it stop here? Okay, why doesn't it go down like this? Okay, why doesn't it keep on going like this? So the Pareto optimal front is nothing but a constraint boundary. Okay, so it is some parts of the constraint boundary which is converted to criteria space, or some part of the constraint boundary which is converted to F1, F2 coordinates. So we'll consider our previous example. So minimize this objective function F1 and this objective function F2. So you'll remember that F1 is coming like this and F2 is coming like this. So A is the solution for F1 alone and C is the solution for F2 alone. Okay. Okay, this is the same thing. So A is the solution for F1 alone, C is the solution for F2 alone. So let us convert this constraint boundaries from X, Y to F1, F2 coordinates. So what they're saying is that every point on this constraint boundary must be converted to F1, F2 coordinates. So how it is done? It is shown with this point C. So point C is 6, 1. So X is equal to 6, Y is equal to 1. So it is converted to 8.54 and 4 in the F1, F2 coordinates. So C61 is converted to C 8.544 in F1, F2 coordinates. Okay. So C61 in XY coordinates is converted to C 8.544 in the F1, F2 coordinate. So every point here must be converted to F1, F2 coordinates. Okay. Okay. Okay, so all these points here are converted to F1, F2 coordinates. So this point B comes here. Okay, this point E will come here. This point F will come here. Okay. Okay, and any points in the interior, like X, Y, Z will come here. Okay. So you can see that these are all dominated points. Okay. And this lower line is the non-dominated. Okay. So it is nothing but this constraint boundary which comes as the Pareto front. Okay, so this is also some same type of thing. This is F1 minimum, okay? F1 minimum is this one. And this is actually F2 minimum. Minimum of F2. This is, okay, so this A will come here. This C will come here, okay. And this B will come here. Okay. So you can see that A corresponds to F1 minimum. Okay, so A corresponds to the lowest possible value of F1. That is around 5, I think. Okay, 5. So you can see 5 here. And C corresponds to our lowest possible value of F2. That is 4. Okay. So how do you identify which is the Pareto optimal front of this curve? Because this curve will actually go like this, okay? It will go like this. So which part of this curve is Pareto optimal? Okay. So this curve will go like this, okay? So this part Pareto optimal, is this part Pareto optimal, is this part Pareto optimal, this part Pareto optimal. So it is very easy to get this boundary, okay? So you just convert the constraint boundary into F1, F2 coordinates and you get the entire boundary of the F1, F2 curve. But out of this, only one part is the Pareto optimal part. So here it can be shown that from A to C is the Pareto optimal part. Okay. How do you know that? So you can draw these sectors. You can see that starting from A, if you draw this sector, there is no points under this. If you take a point here, if you draw the sector, there is no point having F1, F2 values lower than here. So similarly, if you take the point C and draw a sector, you cannot find any other point with F1, F2 values lower than C. Okay. Okay, but if you take a value y here, if you draw this sector, you can find all these points are there which has lower F1, F2 values than y. So y is not Pareto optimal. So similarly, if you take a point Q here, if you draw this sector, you find that all these points are having lower F1, F2 values than Q. So Q is dominated by all these points. So Pareto optimal the part is only from A to C. So in a simple case like this, we can graphically obtain the Pareto front. But if there are many constraints and many design variables, the front has to be calculated using numerical methods like genetic algorithm. So these are some standard definitions which is not very important. In fact, you already studied these definitions by now. So what is strongly Pareto optimal point? The point x star is strongly Pareto optimal if there is no other point x in that space which has a better minimum values for F1 and F2. This is what we already saw. So this x star is said to be strongly Pareto optimal if you can't find any point below it which has lower values for both F1 and F2. So a point x star is weakly Pareto optimal. Okay, so this is X star. It is weakly Pareto optimal because you can find a point X1 here, which is what is say whose F2 value is same, but F1 is better than X star. Okay, so this, you know, um, F1 value for X1 is better than for X star. So this is called weakly Pareto optimal. Weakly Pareto optimal point means it has the advantage of being minimum only in one value, F1 or F2. Okay. These are some standard definitions. Then lastly, there is a, I think we'll stop with this slide. So concept of utopia point. So this is highly important in multi-objective optimization. This utopia point concept is used in several algorithms. Okay. So what is utopia point? Utopia point F0 is the point you get the simultaneous individual minima of F1 and F2. So you can see that at this point F1, you get the individual minima of F1. That is, if you minimize F1 alone, and if you minimize F2 alone, so those results are got at the utopia point. So at the utopia point, you simultaneously get F1 minimum and F2 minimum. Okay. So it represents the lowest simultaneous minima of both objective functions. But because the objective functions are conflicting, Pareto front cannot touch the utopia point. Okay, because the objective functions are conflicting. So Pareto front can either obtain F1 minimum at A, or it can obtain F2 minimum at C. Okay, so either A or C. Okay, it cannot reach both A and C simultaneously. Okay, so what is the use of finding the utopia point? Okay, the advantage of this utopia point is that, first of all, you can locate the utopia point easily by finding this F1 minimum and F2 minimum and drawing these lines and getting this utopia point. So earlier I said that all these points on the Pareto optimal front are equally good. Okay, but that is very confusing. You cannot tell a customer that all these infinite points are equally good and you can pick one of them. So from a practical point of view, the point on the Pareto front having closest distance from the utopia point can be ideal design choice for the engineer. So from the utopia point, you draw a circle which just touches the Pareto optimal front. Okay, and this point can be taken as X star. Okay, so it is closest to the combined minima of F1 minimum and F2 minimum. Okay, so this combination of F1 and F2 is the best choice for the engineer. Okay, so this is how the Pareto optimal front is used in practice. First, you generate this entire Pareto optimal front with genetic algorithm. Then you find the utopia point. Then you draw a circle from utopia point just touching the Pareto point. Then you find the point X, which is closest to the circle. So that X is the best point on the Pareto optimal front. So that can be given to the consumer as the best point. Okay, we can stop here.
Sir, one query.
Ah,
For two conflicting objective functions, will the Pareto be linear anytime?
yeah, if it's a multi-objective linear programming problem, you will get
Okay,
linear Pareto. And that we'll see later. In the worked example, it is there. Okay.
understood, sir. Okay.
So if the objective function is linear and constraints are also linear, then the Pareto optimal front will be made of straight lines.
Sir, what
Okay.
can you do for weak?
Huh? Hello?
Can you go to previous slide, sir?
Okay, okay. Let me make full slide. This one.
What will we do for weekly Pareto optimal
Oh,
point?
then it will be difficult. Then I think you have to choose this point. Suppose you have x1, x2, you have to choose this point. So this is having lower f1. It's having lower f1 than this.
Sir,
Okay.
sir, next slide, sir. Point of Utopia will be away from the Pareto front. So
Yes,
it will be away from the objective functions, both the objective functions, right, sir?
No, it will be away from the feasible region. Out of so all these points are from the feasible region.
Feasible, yes, sir. So it will be away from the feasible region.
Yes.
So if we know the weightage of which function we have to give more weightage, suppose if we have two conflicting function and if the designer knows that I have to give 80% weightage to the strength, not to the cost.
Yeah.
20%.
Then that will only shift here. Okay, if you give 50% weightage, you will get here. That I'll teach you later. Effect of giving W1 F1 plus W2 F2. So that is another method. If you give 50% weightage, it will come here. If you give say 80%
weightage,
80%, 50%, it will come here. 80-20.
Okay, sir. So in that case, sir,
If you give 20-80, it will come here. Okay.
Understood, sir.
So
Understood.
that's another method that we'll study later. Weighted objective function.
Okay, sir. So in that case, sir, point of Utopia, when it is taken, when
Utopia point is always here.
Yes, sir.
Utopia point is obtained by if you minimize, you have to minimize F1 alone.
Yes, sir.
That's
So
a single objective optimization. You have to minimize F1 alone. See, I told you. Okay, this. Okay. So if you minimize F1 alone,
yes, sir.
then you will get F1 minimum.
Correct, sir.
Then you have to minimize F2 alone.
Yes, sir.
Single objective.
Yes, sir.
Then you will get F2 minimum. So whatever weight is not involved here.
Yes, sir.
So this is the individual minima of F1. This is the individual minima of F2.
Yes, sir.
Okay. So that is how you get these two values.
Okay, sir.
Okay.
Okay, sir.
Next Monday you can.
Yeah.
Thank you, sir.
sir.
Thank you, sir.
Yeah. Worship Allah.
Sir,
Yes.
sir, Monday, do we have classes on Monday, Tuesday, or because we have holidays and
According to IIT, yeah, you tell what is the
Sir,
calendar.
we can have a class from Wednesday, sir. That will be better, sir.
Wednesday.
yes, sir.
So why Monday, Tuesday is
Sir,
holiday?
because of Diwali and some more functions are
So
festival.
you have to check the timetable which they gave you.
Okay.
It
What
is
does that say?
as per 80 calendar, sir. It is working day.
Ah.
So we will be having class, right, sir?
Yeah, that's what I said.
Okay,
Sir, we